Okay, so I'm very happy to give a talk here. Yeah, we are moving to the edge of like agentic AI. So we right now see the language models starting from question and answering and to the language model serve as assistant. Oh, and, and right now we are in the agentic AI, in the edge of agentic AI. And we aim to make the language model or more general like a multimodal language models to serve as an agent and to let this agent can use tools to do the complex planning and to finish some long horizon tasks. But challenge here for today's agent is that today's agent are still frozen. So once you deploy on the like the real world systems, it's unable to grow. Okay, so we would like to treat there are several like fundamental bottlenecks to prevent the current large language model agents from evolving. And the first thing we are discussing is about there are no really good practice ground for this agent to grow. And we seems like if we want to solve some complex agentic tasks, it usually requires the interactive trial and error. You need to have the environment. And if you directly interact with the real world environment, so it's very costly and risky. And so we probably need to integrate some synthetic environments, synthetic alternatives, and to let this agent to practice in. And second, it's about learning from experience. So since once we deploy this AI agent right now, it cannot improve. And if you want to solve the tasks from day 1 to day 100, so this model is fixed. And but the human already use a lot of have a lot of experience in using this AI agent. We are not able to, or we do not want to let this every task start from scratch. So we need to leverage past successes and to leverage, for example, leverage the same subroutines to do not need to rediscover every episode when we perform the training. And the third thing is that we need some like persistent memory. And this memory will like to do not let the agent to forget everything between different sessions. Okay, so basically we need some agent that can create their own environment and learning from experience and to build efficient memory. And our goal would like to discuss an autonomous loop for that. And basically, if we want to build this like evolving agent, and we are thinking of like how to create this environment. And we do propose some works to create 1,000 executable environments and include executable and researchable environments. And recently we will release the second version very soon. And we will also discuss the skill-driven learning and try to distill the experience into skills and to see how can we deploy it in the wild. And we will also build the efficient memories to achieve such the good token cost to reduce the token cost for and also achieve a very good performance in these memory systems. Okay. So we will hopefully eventually everything will be a loop and we build the whole harness systems and to support this like the language models to make it to be a better like the agent. Okay. Okay, we will start to discuss the environment and how to synthesize this like virtual environment for this agent training. Okay, and we do the very good reasoning. So these like counter models of performance very good in doing the reasoning and like the math and or code reasoning. So we have a very clear task definition and we have a very good environment. And we actually do not need the real environment, but we have a good environment to have static input and output pairs. And it's also easy to check the reward. So easy to verify the reward for this coding and math reasoning problems. However, we would like to make it like a more agentic reinforcement learning scenarios. So we need to have the environment, and this environment is more complex because you need to interact with the environment and to gain some trajectories and to have a better reward definition to train this model. Okay, so we will focus on how to build this synthetic environment. And there are a couple ways to build like the good training environment. And for example, so we can use language models to simulate this environment. Okay. The challenge here behind this is that if you every time you have this new state, when you made some actions and then you would like to leverage the language model to generate a new state. So this is not very reliable, and you definitely will have some hallucinated state, and it's also very costly to interact with the environment at scale. Okay, and so this will like make the online IO training to be very slow. And also another way is like the human curated environment. And the human curated environments, it's obviously that the cost is very high. So existing like benchmarks like top square bench or top bench have only a very limited handful of scenarios. Okay, so it's quite expensive. And also like the prior synthetic environments, they are too simple to compare with real world tasks, and it cannot like track the real state trends. So we propose like an agent world model to build the environment is that we will leverage the code-based environment, the coding skills of the agent to build the code-based environment to avoid the hallucinations. And also we have the database already in the backend to help us to track the real state. Okay, so we are aiming to leverage the coding ability of the language model to synthesize the environments for tool user agents. Okay, there are 5 steps. The first one, we will do the scenario synthesis, and then based on different scenarios, we can synthesize different tasks. And then we will like to build the database behind this kind of scenario. And also like to have this like interface, and this interface will support the interactions between the language models and the agent. Okay. Sorry, between the environment and the agent. And eventually we will do the NRIL. Okay, I will like discuss step by step. As first step is to synthesize these scenarios. And for every scenarios, okay, so we would like to describe an environment. And for example, like a shopping platform. So which is to have a suite of tools for this agent to complete a specific set of tasks. Okay, so we will start from 100 seeds. And from 100 seeds, we can leverage this like language model to generate different kinds of scenarios. Okay. And this is the seed is the only thing that the humans need to provide to the language models, and then these language models can generate the scenarios. And we show like some distributions of these categories of these scenarios from the speakers. And we have the workflow in e-commerce, bulking, billing, and all these kind of like scenarios. Okay, so we will first have the scenarios, and these scenarios will describe by the language models. And second thing is about the second step is based on these scenarios. For every scenario, we generate 10 tasks for each scenario. And in total, it will have 10K tasks. Okay, so these tasks are the requirements to define this kind of environments. For example, we have multiple tasks. This environment can support this kind of tasks. Okay, and then we would like to prompt the language model to generate the tasks based on the scenario description. One example task, for example, the scenario is like an online bookstore platform, and we will generate a task to, for example, to search the book by the author and filter by a specific price, and then we'll add the cheapest one to the shopping cart and to apply a specific discount. Okay. Okay, so we have multiple tasks to support this overall scenario. So in this scenario, you can play different tasks on this kind of scenarios and then to collect the trajectory. Okay, the third step is that we build a database. So based on the scenarios and the scenarios and the tasks, and we will build the database to support this kind of things. And this database is basically using the language models to read the scenarios and to read the task to design the database structure from like this task descriptions. And you will have this kind of database, and this database will use like a SkillRL style database. And then we can see that there are a lot of keys and the keys and values. Okay, so we can connect like different keys and values. So we build a whole database for every scenario. And we will generate some like a sample data because you need this kind of sample data to finish these tasks. Okay, so in the sample data generation, so we will like to ensure that every task can actually run and can see like what is changed behind this database. So and to ensure that every task is executable. Okay, so we have this database. And based on this database, we build a unified MCP interface, and this MCP interface can let this like an agent to interact with this environment and to play in this environment. So this is basically have this endpoint and with database, and also like every endpoint is like executable MCP tools. And in general, for every it's the average tools that we use, the overall scenarios is like about 35.1 tools, and which is associated with this lines of Python's code to build the whole environment. Okay, so this is how we create this environment. And then when we play with it, how to do the verification. So verification is also like a very important problem that we need to think about to determine whether this like this kind of like the language models is already finished the task or not. Okay, so we basically have the task set and database, and we will use the language model to synthesize some verification code. And this verification code is more kinds of things like a rubric. And this rubric can analyze the change of the initial state and after state, so which is supported by this kind of database. Okay. And then you would like to feed this verification rubric and the results to support to give as like a guidance on the prompt to further support the language model as a judge. Okay, so because like if you only use code alone is not enough for the complex task, so we still need the language model to judge the results. Okay, so this is how we get this reward. Okay, after we get this reward, so we will like perform this like agentic RL. Is that we have the environment and we have the online agentic RL. We can interact with this environment and perform the actions and get the observations and to collect a bunch of trajectories. And then the trajectories will be used as the language model as a judge to get a reward. And then we can use this reward to perform the reinforcement learning and to fine tune this agent. Okay. Okay, so we evaluate, we train an agent on the purely specific environments and to evaluate on this auto distribution benchmarks. Okay, we do the evaluation on BFCLs, V3 on MCP universe and like a total square bench. All of these are like a very popular benchmarks for these two using agent. Okay, and we do see we show a very good results on only when you training on these like synthetic environments. So it means that you train this on synthetic environments, you can perform this stronger on these general auto distribution tasks. Okay. And we also do some analysis on these scaling environments. And the first is to see that we analyze the diversity of these synthetic environments. Okay. So we have like we embed like this information to describe the environment to this including the scenario description database schema and the tool schema, and to embed it using the language model to get this embedding. Okay, and then we analyze the distance and diversities between different kinds of environment, and we can see that in our settings it can still maintain a very good like diversity, but if you have more environments, it can cover more categories. And also we do some like analysis and to see whether this like increase of the environment will enhance the performance. And when we start to increase the synthetic environment from 10 to 500, and we show the results on the 4 billion models, we can see that over on every benchmarks, all benchmarks that we can get a performance increase when we increase the number of environments that we can use to train this model. Lastly is that we do the analysis on the reward design. So we first use the fully language model as judge, and also secondly use like the code-driven judge to use the code to design the prompt, and then to analyze the change of the state on this like the database. And further is to use the code augmented LM judge, and we can see that the code augmented LM judge do provide some complementary information to benefit the language model to serve as judge. Okay. So this is the first thing that we want to build the environments. Okay. And we have the synthesize to have the seed names to get the environments, and we only need the LM coding ability to write a lot of codes to define this kind of like the environment. And we can scale it, and also it's very good for this large scale agentic training. And we also like to verify it by using the code plus LM verification and to provide more precise and flexible verification to get the reward. Okay, so any questions? Okay, if no questions, we can move to the next one. Okay, right now we have the environment to train this agent. But as we discussed before, it tackles more tasks in the training. It still needs to rediscover the same subroutine or sub-skills from scratch. So we need to think about how can we distill this accumulated experience into the reusable skills. And we will then discuss the skill-driven learning from the training, from the post-training and to the test time training. Okay. To distill this experience into skills and to deploy it in the wild. Why skills? And in this like model training, so if you do not have any memory, so for every episode, so you get some experience, but you still need to start from like purely zero, so you do not get accumulate this knowledge. And there is also no knowledge transfer across different tasks. Okay, well, what if we can store all route trajectories? Okay, route historical trajectories. So the challenge here is that if you store all actions, all trajectories that you already used in this IO training, the challenge is that it's quite verbose and noise and unstructured. Okay. And it's very easy to fill up the context window. Okay, so for every model, it still have the limited context window. And we would like to discuss skills and to make this learned experience to compact it as reusable skills and to compound this knowledge over time, and also let this knowledge can be transferred across different tasks. Okay. So in this vanilla GRPO and in this vanilla training process, and this knowledge doesn't accumulate over different kinds of over different types of scenarios. Okay, so this knowledge didn't accumulate, and we propose SkillRL to compound this knowledge. So you would like to distill this episode to make it as compact and reusable skills. And you will build this like a skill bank, which contains the general and task-specific skills. And the skill library, the skill bank will co-evolve with the reinforcement policies at every epoch. Okay. So this is like a short comparison for this training steps. Okay. Starting from 0 to around 140 training steps. And we compare the SkillRL versus the vanilla GRPO, and we do see that providing the skill can significantly speed up the training progress. So we see that this red line versus like the vanilla GRPO and the blue line. Okay, we can significantly increase this performance, the training performance, success rate, as well as it can significantly speed up the progress. Okay, and it's also interesting to see if you do like this GRPO versus the memory, so it will even like kind of like it can speed up the progress, but it will like to make it very harder to leverage this kind of knowledge to achieve the higher success rate. Okay, so you use SkillRL to further can achieve the high ceiling and the faster convergence. We will discuss how can we build this SkillRL in this 4 training pattern. Okay, so there are 4 steps. One step is optional, and the 4 steps we use to build for this SkillRL. And the first thing is that we will leverage the base model. This base model is student trained on the scenarios. Okay, so this base model will first to interact with the environment, and we can collect a lot of trajectories. And these trajectories can be categorized as like the successful trajectories or failure trajectories. Okay. So this base model, like a human model, so you interact with this environment, and this success trajectories can extract what works and why. And the failure trajectories can be used to help us to analyze what went wrong and how to fix it. Okay. So this is for this both the successful and the failure trajectories. Okay. And after you get these trajectories, we will put it into a memory or we will store it. And then we will use the language models to distill the skills from these trajectories. Okay. So you already have some base trajectories at the initial stage. Okay. So you will first have the initial stage of the skill bank. And this will categorize as the general skills, and which is can be shared across different tasks, and it's always active. And the task-specific skills is only retrieved for every task. We would like to say if this base model is very large, and for example, you use like a Kimi 2.5 or 2.6, so this is super large base models, and itself can be used to distill these skills. Otherwise, for very, very small model, if you want to train, for example, like a 7 billion models, you probably need a larger models to distill the skills and to leverage the GPT or any kind of larger models to distill the skills. Okay. And both like category of skills, we do see that they are useful. And in our application study, and if we remove either general or like the task-specific skills, it will cause the performance degradation. Okay, the third step is the cold start continuing. And this step is only used, so you have models interact with the environment and collect trajectories, and then use the skills to collect the trajectories, to collect the data to do the supervised fine-tuning. The goal for this stage is only to collect some data, to fine-tune the models, and to teach the model how to use these kind of skills. So similarly, if you use the fine-tune on very large models, okay, so like Kimi 2.5 or 2.6, this size of models is not necessary because the model itself already know how to use skills. So the cold start supervised fine-tuning is a necessary step only for the if you have base model is very small. Okay. And the last step is that you would like to leverage this like supervised fine-tuning model to further interact with the environment, to use skills and to enhance it. And then these evolved models will further used to have the trajectories, have the failure trajectories, and we will like to leverage the current failure trajectories to summarize new skills. Okay. So in the training step, so right from the, for example, from the training iteration 1 to training iteration maybe 50, and they need some like different kind of skills. Okay, different kinds of skills. So you would like to enlarge the skill bank, and basically to update the skill bank, targeting the current failure skills, and the skill bank is co-evolve with the policy. So as the policy improve, the skill bank will be also updated. Okay, this is the 4 training pipelines for the SkillRL. And let's see how this skill bank evolve. So here the skills will grow from like 55 to 100. So initially we have 55 skills, and after we finish training, we right now have the 100 skills. And here is to evolve during the training, so the general skills increase and the task-specific skill also increase. The success rate, and with and without skill evolution, and we can see the high success rate. Okay, with skill evolution, and have the skills to accelerate this like convergence. Okay. For the performance, and we do see the SkillRL performance very good compared with any memory-based method. So you use memory to store all these trajectories and then retrieve. And like the Mem0 or SimpleMem, which is like some very popular like memory systems. So you using skills can significantly perform better. And compared with the vanilla GRPO, and the skills can also perform good. So we evaluate on some like basic tasks, like in AlphaWord and the web shop, is to all this for the action agent tasks. And we also evaluate the results on search QA. Okay, on search QA. is in the search question answering, we evaluate on the single hop QA and the multi-hop QA. Okay, and we have two data would be the in distribution. The NQ and the hot QA are in distribution, and all other performance are out of distribution performance. We initially do not expect to see very strong performance because for these search questions may not need the skills may not super helpful, but it do show a very good performance compared with other very strong baseline like search O1, search R1, all these kind of baselines. Okay, so we can see that SkillRL can still significantly increase the performance, okay, by leveraging skills into the training. And eventually, the ablation study do see that you need a skill library, you need to have some hierarchical structure, and you need the code start super fine-tuning to let the model know how to use skills. And the token efficiency compared with low memory that using skills can also reduce kind of 10 or 20% of tokens during the training stage. So the SkillRL use a few tokens that low memory baselines and achieve significant high performance. So some case study. And like this web shop or Alpha World, and we can see that we have some retrieval skills, we have general skills, task-specific skills, and this general skills, for example, prioritize the all keywords when you finish some tasks, and then focus on some key query. This is for some task-specific skills. And we can see in this web shop or Alpha World, we have different kinds of skills that to use to help the models to better finish the task. Okay, to finish the task. Okay, the takeaways for the SkillRL is that we will distill, so to learn from both wins and mistakes, to compact and as the reusable skill patterns, and to organize it as general or task-specific skills, and to further evolve. Okay, to make these models to get a better performance, to get the post-training performance. Okay, so the SkillRL to help models to adapt during the training. So what here? We deploy this model into one. Okay. So to build some models after training and to improve it, to make it models to evolve. Okay, to evolve 24/7. And we need to have the strategy to make this model to self-evolve. And there are some approaches that to leverage the memory-based systems to store everything, and the skill-based systems to extract skills to let the model to evolve. Okay, and also to use reinforcement learning training and to train on some data sets and to make these models to evolve. And we propose the MetaClaw to unify all these kinds of strategies to do the skill learning, to do the model improvements, and to do the smart scheduling in purely in one systems. So the pipeline for this MetaClaw is that we hope the models to meta-learn knowledge during the continued meta-learning process. And basically, the inner loop, okay, the inner loop is that we would like to make this model to do the fast adaptation. And basically, is to do the skill-driven fast adaptation. And in the skill-driven fast adaptation, our goal is first to let the model to analyze the failure trajectories with the language model as a solver. Okay, and then you can get this the failure trajectories to generate skills. And then the generate skills can be directly injected into the system prompt, and there are zero service downtime. And the effect is that there are second-minute time scale, so it's very fast to integrate into the models. Okay, so basically is that you have the own cloud, and then you detect its build time, and you will do the fast adaptation, do the inner loop adaptation. Okay, and this skill set, collected skill set, will serve as a meta knowledge. Okay, so that can be used in future tasks. And for example, there are one distilled skills is that we need to do for example, when you manipulate these file systems. So we need to back up before modifying any files. And for them create a copy before modifying any existing files. And if there are missing, so you need to verify backup and that type. Okay. So another stage is about to do the opportunistic policy optimization. in this opportunistic policy optimization, is that, okay, so we do the interview, okay, you get the skills, right? And then you collect the data. You also have the trajectory. You have the natural interactions with systems. You have this conversation results, okay? And this conversation results will be used, okay, we will do some visual control. And okay, you have the, after you distill the skills, you will apply the skills on the future tasks. On the future task, like we do the meta learning, we have the support set and the query set. Okay, so we do the like skill fast application on the support set, and we have another query set, and that can be used to evaluate whether this actual skills under the current parameters can improve the performance, or can improve generation. Okay. And then we do this opportunistic policy optimization, and in this optimization are purely new tasks. And here's the ways to do it. Like we do the JPL with Cloud LoRa fine-tuning. Okay. Here we use like the Tinker from the Thinking Machine Lab and to fine-tune the models, fine-tune the very large scale models. We do fine-tuning on the Tinker on the Kimi 2.5, and recently fine-tuned on the Kimi 2.6, and also like we fine-tuned on Q1 around 200 billion kind of models. And we define the reward as the progressive reward model. And we will detail the reward in the second slides. And this is very, very important steps when you would like to deploy it in the web. Okay. And this detection is to detect some like 3 times and to perform it. Okay, to perform it. Okay, so the key important when you do the policy optimization is how to perform the progressive reward model. And we need some like good rubrics to define for it. And the rubric is here, we define the rubric. This is still an ongoing project, but we initially defined this rubric to use judge to see that whether this each agent turn can finish the task or not. And so we have a positive one and success, or like negative one and failure, or 0 is ambiguous. And we will have 3 judge to do and then do the majority voting and to reduce this noise. And this rubric is basically to evaluate whether this generated response successfully address this given instruction or not. And we do not currently not consider the follow-up turns because it's hard to justify whether this follow-up turn is still for these questions or for the early questions or for later questions. So we currently is only do the next turn to do the PRM. Okay. And this output would be like 3 types of scores. And the 4 pipeline here is we eventually want to have a better policy, and then we will have more informative failures from like this trajectories and have richer skills, then to have higher reward trajectories and have a better policy. And eventually we can achieve it to make this open cloud to personalize to every users. And the MetaClaw is already be extended beyond the open cloud. And we already have the multiple supported personal agents for like open cloud to neural cloud, like all these kind of supported personal agents, and also have multiple supported providers and platforms, and also have some backend IO training infra, and to provide the LoRa training, okay, and to let these models, let this approach can be trained on very large scale models, okay, instead of using the local GPUs to train, so which is impossible for any kind of labs. Okay, so we evaluate the performance on this like command used like tasks, CAI tasks, and we first generate. We cannot like collect so many real data to generate this evaluation suite. So we only synthetic using the cloud code to synthesize different kinds of like the evaluation. So we have like a part 2 and part 1 and part 2 to have the exclusion heavy tasks with increasing difficulties or rule-based tasks, okay? And we do see like if you apply the MetaClaw can improve the performance, okay? Improve the performance. So we have skills and you have this performance with the IO. So we do see like the CFO do helps in this kind of scenario, but there are so many further improved space is that we already introduced the for example, memory systems into the MetaClaw. We already use we'll introduce the routing systems into the MetaClaw. And all these kind of things, and also like how to store the skills, how to evolve the skills, and how to serve, for example, like how to open the skills. You cannot like to put all the skills exposed in the same time. So you need to better store it and better retrieve it. Okay. So there are a lot of like engineering tricks can further improve the performance. And we also apply MetaClaw to support the systems that we propose to do this auto research. Okay, to do this auto research, it's basically you have some ideas and then to generate some papers. And this is like in the autonomous research pipelines. And when we apply the MetaClaw, so there are since there are so many stages. Okay, for example, the stage to help you to write the code, to stage to help you write the paper. There are multiple stages. So when we apply the MetaClaw, we can see with the help of skills, we can like to reduce the stage retry rate and reduce the refine cycle, and to also increase the stage completion. So this is also quite useful if you deploy to any kind of like agentic systems. And it also can be easily to integrate to any agent systems. Okay. The takeaway here is that for this MetaClaw, you do the fast adapt to learn from the mistakes, and no downtime, and skills can transfer across different tasks. And also like we do the opportunistic the training, and to train on these cloud systems. And as there are no GPU, low local GPU is needed, and the skills model can improve each other. And also we do the versioning controls and to make sure this is the real like a meta learning to enhance the generalization abilities for this kind of like models, and to have the smart data management to use the fresh data for training. And we'll discuss this outdated experience automatically, and to see like how these accumulated skills or like updated models can further improve to evaluate like this improved models to see how it performs on these new tasks. Okay, on the purely new tasks. Okay, so the SkillRL and MetaClaw will solve the risk discovery, but skills shared across tasks, and that we still need to have the personalization or like the memories to have the interactive content. So we need a memory system, better memory system to spend many sessions and adapt to individual users. And we later propose the SimpleMem, and this is actually something we propose. We have a papers on January, but it's kind of like outdated at that time. So there are so many competing memory systems, and we recently also have a better feelings about better insight about how to design this memory system. But I will also briefly discuss about it. So in this SimpleMem, so we aim to achieve as efficient memory to reduce the token cost for these lifelong memory systems. And we can see the skills, it solves a lot of problems, okay? But it's still missing is that we need some memories, especially for cross-session memories. In our experience, single session memories is single session ones may be more useful to extract skills, but cross-session ones, the memory is very important. Okay, so for these cross-session memories, so you need to build up memories when you talk to across different sessions, and especially for some long conversation histories, so you need a longer context windows. Okay. Okay, so we have the different types of things. We need to have memory, especially for the cross-session memory to store the knowledge. Okay, to store the knowledge. Okay, so for these kind of things, if you fully context, do the fully store or full context storage for these memories, this may not be sufficient. Is that basically the stuff in package into the context, and this may have context inflation, redundancy, or middle context degradation. But recently, we are also discussing whether this full context storage would be very useful or not. So sometimes maybe the most useful way is to store every information, so you do not have any information loss. And another way to have people do is to interact iterative reasoning filtering. But I guess this is quite a high cost, so you have the multiple LM call per query. And we propose SimpleMem. And this SimpleMem has the like a three-stage pipeline. Okay. First, at the like a semantic layer. So we will map this entry to a dense vector space, okay, using the embedding models, okay, to capture this abstract meaning to enable this like a fuzzy matching. And second, we'll do the indexing. Okay, you will first to do this like a filtering to filter some noise and to get this memory unit. And then we will have like indexing, and this indexing would be used to do the retrieval. And we perform three views of indexing. The first one is about semantic layers. So you will like to leverage the embedding models to get the dense embedding for this conceptual similarity retrieval. And the second one is about lexical. And we will do the sparse features for the precise keyword matching. So you do the kind of keyword matching for that. And third one is about symbolic. And in this symbolic, we will like to leverage the structured metadata for this like knowledge lookups. Okay, so after doing this indexing, you will know for a new knowledge, you can find the similar like the memory unit. And then we will do this like online semantic synthesis. And in this online semantic synthesis is that you have some new unit or new context, and then you get this like information, and then you can find the most similar the unit. Okay, so unit, and to synthesize this kind of knowledge. Okay, to consolidate these related memory fragments, and then to merge into the high density unified entrance. Okay. And lastly, we will have the intent-aware retrieval planning. Okay, so you have the user queries, and you will first analyze this intent to infer the query scope and the complexity. And then you will do this like a multi-view retrieval. Okay, from this like query types, you will do the parallel search from the three types of indexing. Okay, and to further get this similar knowledge to further benefit this output. Accuracy. And we do see that this SimpleMem performs very good compared with similar memories proposed in 2025. Like the MEM0, AMEM, LightMem, all these types of that. Okay. So MEM0 is raised a lot of money, but we do think the open source version is super bad. Okay. So and also like the similar things, like also like the CloudMem. So it's also kind of like things that is very popular, but we do show the very good performance in compare with the SimpleMem with other memory systems. Okay, with our memory systems. And also we can see that our memory systems, the SimpleMem, can significantly enhance this like retrieval. We compare with the retrieval speed and compared with MEM0 and LightMem, and we can see that the SimpleMem is super fast in doing this like memory construction and memory retrieval. And our ablation study also shows that the importance for every component is the SimpleMem. Okay, in the takeaway for the SimpleMem is that we do the compress. Okay, we have a semantic gating. Okay, and also like to do this like a temporal normalization or something like that to compress this useful information. Okay, so we'll also do the synthesize, and to you have the new knowledge, and you would like to synthesize your new memory information, new context. You will synthesize with the existing memory units. Okay, and then further to do the retrieval. Okay, so we do see that's a significant increase of the SimpleMem compared with the other memory systems. And we do see the performance around the 26% over MEM0, 64% over CloudMem. We recently also extend the SimpleMem to the multimodal SimpleMem, and by purely using the auto research to find a better memory structure for every benchmarks. And it even achieves the more significant gains compared with this like memory systems. Okay. Okay, this is what we would like to talk for today, is to build the environment, to build the skill-driven training, and to build the memory systems. Okay, thanks. Any questions?
Agents, directions, this is very interesting point. I read some of the paper previously, so I'm curious about how do there is a difference between the deep learning and the foundation models. In deep learning, we modify the parameters to learn some knowledge like the loop for faster or task-specific learning, and the outlook, the methods will be used to update the global parameters. In foundation models, what should we learn in the context of like if we would like to learn some task-specific knowledge, what should we modify here? Because it is infeasible to modify the model parameters. Even use LoRa is a very large computational task. So what do you think is the additional points to apply learning here to compute?
Okay. So basically, we would like to think you can treat the foundation models as the new types of deep learning. So previously, or like the agent is new types of deep learning. Previously, we did like the meta learning things on like the purely deep neural networks, right? On the small scale, like neural networks, maybe the largest one would be like using some small transformers, like with VIT or these kind of things, and to perform the meta learning on it. You can change them. You can change the weight to the inner loop. You can do like this like rule based or like the embedding based similarities to say the lazy learning on this meta learning process. But right now, I would like to treat that the machine learning go back. Okay, so in like 2 years before, well, a lot of people we discuss like a lot of like older machine learning topics that will be less useful. But right now, so all the things will go back. So you can do the continually, you can do the meta learning on these types of like new areas. Okay, you can perform as a meta learning or continually. You can transfer the knowledge across all these kind of things. Okay, I would like to think. So I would like to treat this kind of like in this like new age of like the agentic AI or like these foundation models. This kind of things would be you retrieve the knowledge would be kind of like that could be treated as one in the loop. So basically, you retrieve the useful knowledge, and this kind of like a database or like a skill base or this memory base would also be treated as one type of meta knowledge, or like a more generalizable meta knowledge, and you retrieve some knowledge and to serve as a prompt and to prompt this model. So it's a kind of things that is already made as like personalization. So as a task adaptation, right? So basically you have the similar, you have the queries and then you retrieve this information from like the skill set and then to use it, serve as a prompt. And this is the things that you already do are kind of in the loop.
So can I understand that the skills or the previous elements that the class specific knowledge or the surrogate of the
yeah, this is the types of kind of like a more generalizable version of like this model parameter adaptation.
So actually we all know that LLMs or foundation models are very sensitive to the prompt. So maybe sometimes when we just retrieve memories from long memory data from the database and we add it as the prompt, this may steer the behavior of foundation models. So actually the mechanism, the underlying mechanism of the index is still unknown. So would it be a potential direction that we leverage both skills and the behaviors in next learning as the like task specific or meta?
Yeah, this is more like in the loop. You can make it adaptation, but the meta knowledge beyond these parameters, the purely language-based things could be also one type of meta knowledge. We previously discussed the meta knowledge or meta models is something that we do it, for example, model initial parameters, the learning rate, or any kind of things. And in these kind of areas, so we right now see the more language-based things could also be types of the meta knowledge or one types of meta model. And the good thing is that this kind of knowledge could also very easy to be transferred across different tasks, and it's more transferable, and it can also avoid some kind of forgetting. So we discussed a lot of forgetting when we do the continuous learning previously, but right now, if you have the like a better abstraction, better things, better like skill systems, and you can make it like really transferable across different tasks to enhance, to make it more generalizable. Yeah.
So my friend, actually, I didn't have a lot of experience in programming. I noticed that when one of your work mentioned the SkillRL. In that case, you use both modifiers and the diagram as a judge, right? So, do you use score as the reward or the?
We use score as reward.
Yeah. Here is my question. Currently, actually, the reward signals are usually recognized as very sparse signals, and such signals may result in some instability or something else. So, and at the same time, when you from our already fast learning, you also doing many, the self-evaluation operations. I'm curious about do you think the self-evaluation and the smart signals are the good signals for the?
Yes, this is a very good question. But actually, this definitely as a language model generates reward signal is not ground truth, right? Not ground truth. So it will have bias, and this kind of bias will also amplify some mistakes. So this is some we need to provide some like alternative strategy, not like alternative, it's like better strategy, for example, to mitigate or to reduce some noise, for example, using like multiple language models to score it, to do majority voting or any kind of things to enhance the reliability of like this scoring or this like rewarding. But it's still possible that especially you apply it in the real world scenarios, and this model, if after you do multiple fine tuning, and this will do the reward hacking, or this will mimic the things happens in the language model. This is all possible things. So we still think that using, but this is quite an open question. I think you how to define better reward systems and to make the IO to really capture the human preference. This is a purely open question. Probably we also need to using the purely IO or enhanced to do the reasoning, or like to leverage some like preference optimization to do the combination of like these kind of things, and to find which is better ways to make this better. But this is still an open question, especially when we have our practice is that you apply to the real world scenarios, especially we need to, for example, from our conversations, we get some reward. This is super hard. And there are no ground truths, but right. If you have math, it's relatively easy to have the ground truths, but it's quite open questions. Yeah.
We talk about self-evaluation. In this year, or let's say in recent months, a more popular topic in agent of foundation model is self-distillation. In this case, it usually assumes that the current models provides much better like responses compared to the previous one. So they use the current response and the feedback of the previous step like model for the next step evolution. So as we just mentioned that self-evaluation will not be very stable, or
I think it's kind of stable, but the things is it may amplify some kind of bias. This bias may not be reflected from benchmark, but yeah, it do have kind of bias.
That self-display is not very good and cannot from most next PO method. So do you think that relying on the foundation model themselves can help train better models?
It's possible if you do the self-evolution, but maybe a better way is also do the crowdsourcing, so you can use multiple external models, and this can provide like another angles to support it. It is not like a purely self models, but you still need some external ways to calibrate it. Yeah.
Okay, I have a quick question. So in current the knowledge retrieval system, do that operate online? For example, new knowledge come and need to update.
Yes, we can do it purely online.
Due to the time limit, so we just end here. And thank you for attending. And okay.
Thank you.